All right, now that we understand how to take covariant derivatives of tensor fields, let me move on to the next item on the agenda, which is the idea of parallel transport. This is a key idea in general relativity, and it's very important that you understand what parallel transport means of a vector. Parallel transport of a vector means. Now, the essential crux of the idea is that on a manifold, these tangent spaces, you have at each point there is a tangent space, and there are vectors living in the tangent space. These two tangent spaces are completely independent. They're separate vector spaces. And we cannot compare a vector living here on this tangent space to a vector living here. Let's say v prime living on this second tangent space, because vectors living in two different vector spaces can never be compared, right? We can only compare vectors. We can take sum or difference of vectors which live on the same vector space. The vector addition is defined to be valid only in inside the vector space. We cannot add or subtract vectors living in two different vector spaces. Okay, but it turns out that affine connection is such a miraculous thing which allows us to compare vectors in different tangent spaces of a manifold. Okay, you have an affinely connected space or a manifold, and you have two different tangent spaces. Affine connection allows you to compare a vector v in one space to a vector v prime in another tangent space, okay, or another point. So, it can be used to define something called a parallel transport. So again, this is the manifold. This is the affinely connected space, and let's say we have some curve x of lambda on the manifold, and let's say at some point on the curve we have a vector living at the tangent space at this point, which we call the vector v. Then this notion of the affine connection, which we learned, the nabla, or equivalently the gamma, allows us to transport the vector parallel to itself on that curve. These are approximately parallel, but I'm trying to show that you can translate the vector along this, or transport the vector along this curve with some notion of being parallel to itself. Then you can see, you can tell me that all these vectors which I have drawn on different parts of different points of the curve, they are all independent vectors living in different vector spaces. So how can I claim that one is parallel to the other? So let's see how that is done. The idea is that affine connection allows you to compare different vectors on different tangent spaces. So in particular, I will say that the significance of the affine connection is that if you take two vectors which are living in two different tangent spaces, then if they are infinitesimally close points, if those two tangent spaces are infinitesimally close points, then this v prime is v plus some d lambda times or dx times dotted with del mu acting on v. Yeah? So this del v or nabla acting on v gives you difference. So this nabla of v, in some sense, this covariant derivative is defining a difference between a vector in one tangent space and a version of the vector in the other tangent space. These two live in two, but this is measuring some kind of difference between them. Okay, in the infinitesimal limit. When these are infinitesimally close, then del v you can think of as defining difference between two infinitesimally closed vectors lying in different tangent spaces. There is no point in defining infinitesimally closed vectors, but this del v can be thought of as measuring difference between two vectors living in infinitesimally close by located tangent spaces. All right. So then, parallel transport means because the vector has been transported parallel to itself, or these two vectors are parallel, then the difference between them is zero, right? If two vectors, their components are the same. But when we say two vectors are parallel, we mean their components are the same. Actually, you can take proportional because one can be larger, but we are going to assume that the difference between the two vectors is 0, or the covariant derivative acting on them is 0. So this T dot del is very important because we are defining parallel transport on a curve in which T is the tangent vector to the curve. Okay. So T dot del measures the affine derivative, or covariant derivative along the curve. So if the covariant derivative of the vector along the curve vanishes, then we call that parallel transport. Now you can ask, what do you mean this vanishes? Because we know in general a vector v will not vanish, because if I take this vector, this is not necessarily 0, right? So how do you define parallel transport in that case? Actually, the pedantic thing to say is that I introduce a new vector field, or new vector v prime of lambda, such that given v here, v prime of lambda here satisfies this condition. V prime of lambda is defined for all values of lambda. So v prime of lambda, which is the parallel transported version of v, T dot del, v equals 0. T is the tangent vector. So let me write this in components. So if I write this in components, so this will become T alpha, or T dot del will become T alpha del alpha. And then we have to operate on V. So a del alpha acting on V we have already written. So we have to take the muth component of this. It means you have to take T alpha times del alpha V, and then muth component of that. And this we already have worked out in the previous slides, which gives you something like this. Okay, so this equation in the bold fonts is called the parallel transport equation, and this is the component version. And all the indices have been indicated. Okay, so as I said, physically this represents a vector which has been, as a starting point, we have some vector, and then we construct a new vector at each point, which satisfies this equation. Okay. Now that is not necessarily equal to the value of the vector. This new vector which we constructed by parallel transporting V might not be the actual vector field itself, but a parallel transported version of the vector field. All right. So now this parallel transport equation, or the notion of a parallel transport of a vector parallel to itself along a curve, can be used to define straight lines on a manifold. Okay, how do we do this? Well, in the parallel transport equation, you take the vector which you are parallel transporting along the tangent to be the tangent vector itself. So you just have a tangent vector, try to transport is parallel to itself. Okay, so in this case, in contrast to the previous case where a curve is given, here we are trying to determine a curve such that which is obtained by parallel transporting the given vector parallel to itself. Okay, this is the equation of a curve. If we do that, we get this equation. So in this case, unlike in the previous case, we are not specifying a curve beforehand. We're just saying that let's imagine a curve in which the tangent vector is parallel transported to itself, and then what would that equation be? And that equation is this. Now if you solve this equation, you get the answer, and that defines what we will call an analog or counterpart of a straight line on a manifold. Okay, because it is moving in the direction of the tangent. If you think about a straight line, if you take a tangent at any point on a straight line and if you translate it along it, you generate the straight line. So this is how we generalize the notion of a straight line on a manifold or on a affinely connected space. And these are called autoparallel curves. Okay, these are analogs of straight lines. So let me again emphasize that the parallel transport equation, in the parallel transport equation, a curve is given beforehand and a vector at the initial point is given. And then using this equation, you're supposed to construct V at all points on the curve, on the given curve. In contrast, for this self-parallel transport or autoparallel equation, the equation has to be solved to determine the curve in the first place. So one thing you must notice is that this equation looks a lot like the geodesic equation. Let me just go flash to the first slide. Yeah, the geodesic equation, as you can see, which has a second derivative term and then a velocity or proper velocity term multiplied by this Christoffel symbol. Compare that autoparallel curve, you have the exact same thing except instead of the Christoffel symbol, you have the affine connection sitting here. Okay, this is what I meant. This looks a lot like affinely parametrized geodesic equation. Affinely parametrized because the right hand side is 0. This looks like affinely parametrized, except for the fact that in place of the Christoffel symbol, you have the affine connection sitting here. And it will turn out that, in fact, if we use let me remind you that the connection is non-unique. For a given manifold, you can if you have a connection, you can always add a 1, 2 rank tensor to it, and it will be equally good connection. But there exists among all those infinite set of connections, there is a very special one, a unique one, which is called the Levi-Civita connection, in which this becomes equal to the Christoffel symbols. And then this equation for a straight line or autoparallel curve will be the same as that of a shortest distance curve. Okay, these two notions, usually they're different. The shortest distance curve and the autoparallel curve, they're not necessarily the same in Riemannian geometry or differential geometry. But if we use the Levi-Civita connection, then these two concepts get unified. They become one and the same. Okay. So as a result, when you solve this equation, if this is a Levi-Civita connection in which this is the same as the Christoffel symbol, this equation, autoparallel equation, automatically gives you an affinely parametrized geodesic. Okay, as I said, we need to explore what this Levi-Civita connection is. So it is defined to be the unique metric compatible torsion free connection. So big gamma is now, as a result of metric compatibility and torsion free condition, will be a function of the metric and the first derivative of the metric. In fact, when we write that down, when we solve these two conditions and write down, it will turn out to be the Christoffel symbols. So metric compatibility means that the metric is covariantly constant. That is, if you take the covariant derivative of the metric with respect to a vector field x, that vanishes. Now you can ask, physically, what does this mean? We will discuss this later, but for the time being, let's assume that we have taken this assumption that the metric is covariantly constant, that is, the covariant derivative of the metric vanishes. In that case, we can write this in component form, which is this equal to 0. And since I've already mentioned the rules for taking covariant derivatives of tensors, we work that out. This is equal to 0. Okay, so how many such conditions are there? So let me start with the total number of components of a connection. Remember, the connection has 3 indices. And let's say we are in a manifold of dimension d. Number of space-time dimension is d. Then each of these mu, nu, and lambda, these 3 indices, can take d different values. So total number of components of this gamma is d cubed, d raised to the 3 for the 3 indices. Now out of these, the metric compatibility will give you a constraint, which is the number of different combinations of mu, nu, and rho. Now, number of different ways, different values mu can take is d, and nu and rho, because g is a symmetric tensor, the number of different values it can take, this combination can take is d times d plus 1 over 2. All right. So this is, in other words, this is d squared. Let me cancel this out. So d squared is d plus 1 over 2. So these 3 components, which must satisfy this many constraints, and this many constraints which are coming from metric compatibility. Okay, and there'll be a similar constraint which comes from torsion-free condition. So let me define what a torsion is. Now the torsion is actually a tensor. So this is denoted by T, and it's a tensor which is a multilinear, by which, as you know very well, tensors are multilinear maps. So these are multilinear. This T is a multilinear map which takes 2 vector fields and spits out a third vector field. How does it happen? Let me define them, give you the map explicitly. So T, in which if you feed two smooth vector fields, x and y, then this is given by action of T on x and y is given by the covariant derivative of y with respect to x minus the covariant derivative of x with respect to y minus the Lie bracket of x and y. As you can see, if you reverse the role of y and x, the torsion tensor picks up a sign. Okay, T of y and x is equal to minus T of x and y. All right, so the torsion is defined in this way. Again, I'll come to the physical significance, or not physical, geometrical significance of torsion tensor in a moment. But let me just look at what the components of the torsion tensor are. To know what the components are, I must substitute for x coordinate basis element or tangent space basis element, which I have taken to be the coordinate partial. And then similarly for y, I have taken the tangent space basis element nu, which is the coordinate partial with respect to the coordinate x nu. And this will define the T mu nu rho component. Again, remember T takes two vectors and spits out a vector, so it has a component, component and a basis element. So this component is what we call T rho mu nu if I give you mu and nu in place of x and y. So then, if you process this, that is, if you work out the right hand side, this is 0. I'm sorry. This will work out to be 0 because we know the Lie bracket of two tangent space basis elements, the important basis element is 0. So that this term doesn't contribute, but these two will contribute, and we already know the covariant derivative of nu with respect to mu gives you gamma rho mu nu, and this will give you this mu and nu reverse. This we already know. So if we use the coordinate space elements, basis elements, then T is just the difference between their affine connection and its indices swap, lower indices swap version. Okay, so this must vanish. So torsion free condition means this T must vanish, in which case it means that the affine connection is symmetric under swap of the lower two indices. Nu nu equals to nu mu. Okay, something like this. So again, how many constraints are there? Well, rho can take d different values, and mu and nu, as we turned out to be symmetric, so the number of constraints will be d times d minus 1 over 2. Right? So these are the number of constraints. So total number of components of the connection is d cubed. And then the metric compatibility removes some components because there are d squared times d plus 1 by 2 constraints. Sorry, this is 1. And then another d squared times d minus 1 over 2 constraints which comes from torsion free. And if you subtract these two from d3, you will see the answer is 0. That means there are no freedom left and the completely determined. Okay, and this I will leave as a homework. If you start from this equation and try to work out, if you use this symmetry and use this equation, after some manipulation, you should be able to solve for gamma in terms of derivatives of g, and you should be able to show that gamma turns out to be exactly the Christoffel symbol. So, in coordinate basis, the Levi-Civita connection, which is metric compatible and torsion free, is equal to the Christoffel symbol. I emphasize coordinate basis because I could have taken some other basis E mu, in which necessarily this third term will not be 0, so you'll get an extra term. So t equal to 0 might not mean symmetry. Okay, torsion vanishing gives you symmetric connection only if you assume coordinate basis. So I must emphasize that only in coordinate basis, which is what we will use in this course exclusively, the Levi-Civita connection is same as the Christoffel symbol. Please work that out. Again, solve this equation. We're subject to this constraint. All right, now let me slightly go over this the significance of choosing these two conditions, metric compatibility and torsion free. What does metric compatibility lead us? What is the significance of that? Now, it turns out that metric compatibility is very important because, let's say I have the continuity equation. I can write the continuity equation in this way, right? Or I can write it with mu raised and j lowered, that is one form, okay? Now, if we don't assume metric compatibility, these two equations will be different, and this equal to 0 would not necessarily mean that this is equal to 0. That would be very strange because we want to treat covariant and contravariant indices on equal footing, right? In some sense, as far as physics is concerned, I should be able to write my continuity equation in this way or in this way with lower indices. There should not be a difference. It's very easy to check that this would force us to take metric compatibility. So this J mu I can write using raising lowering operation as G mu with J index lowered. And then I can use the Leibniz rule because we have two tensors that will give me two terms, one in which the covariant derivative will act on G and it will spare the J. And the second term from Leibniz rule is when G will be spared and then the del mu will act on J mu. Again, we can use the raising lowering to write the second term as del nu J mu. So this term is equal to del nu J nu plus this extra term. Now for these two to be equal, this term must vanish, which means since J nu is not 0 in general, the only way these two can be the same, or this one and this equation can be the same, is if del mu of G mu vanishes, or metric compatibility. Okay, so metric compatibility is essential. If we have metric compatibility, we can take the G. G will be like a scalar. Del mu will not see G, and you can pull it to the left of the covariant derivative every time. So metric compatibility is very important. It will allow us to treat covariant and contravariant indices on equal footing. Another important thing about metric compatibility is that it ensures that the norm of a vector remains fixed under parallel transport. So if you take the parallel transport and you find out whatever the v square, the norm of the vector, this will again, you have to use v square. You have to write in terms of G nu, v mu, v nu. So this is three terms, and then the Leibniz rule, you have to follow the Leibniz rule to operate on each one of them. It will give you three terms. Two of them will vanish due to the fact there's a parallel transport, but the third term non-vanishing will not vanish unless you take del mu of G to be 0, when this T dot del will act on G. So please do it as a homework, as a simple exercise that in order for the norm of vector to be remain conserved along parallel transport, one must have a metric compatible connection. Now finally, let me look at the torsion tensor. Now, what is the geometrical significance of the torsion tensor? The idea is that consider a point x on the manifold, and let's say I can displace this point x by some amount in this direction, which I'm calling delta. And let's say I can imagine displacing this point to go to a different point on the manifold with displacement by an amount of psi in the coordinate. Okay. Now I can think of this displacement vector delta, which is the small displacement vector located at this point x. And I can parallel transport along in the second displacement direction. So it will go to somewhere like this. So I'm displacing this delta, the small vector along this second guy. If I parallel transport, it will go somewhere here, which is the neighboring point. This point is x plus epsilon. And this point is x plus delta. And I can do the other thing, which is take this epsilon vector, small displacement vector, and translate it in the vertical direction, in the direction of delta. So that will give me another thing, right? So the torsion measures the fact that this parallelogram doesn't close, okay? Measures the failure of the parallelogram bounded by displacement vector and their parallel transport to close. So in general, if you do that, there's no guarantee this point and this 2 points will meet, and there'll be a gap. This gap is proportional to the torsion tensor, okay? So now one can ask, well, okay, but why metric compatibility has a very strong physical reason. We can see why do we need, what is the physical motivation for making the torsion vanishes? Okay, so what if the parallelogram doesn't close? Now it turns out that one can consider a connection with non-vanishing torsion. It is not something unphysical. We can consider it. However, this is going to be entirely equivalent to using the usual Levi-Civita connection plus a new 1,2 rank tensor field, the torsion connection, whose couplings are not universally dictated. Okay, there is no equivalence principle for this torsion part. Okay, some couplings of the torsion to other physical fields. For example, the coupling of the metric to matter field, which is the gravitational coupling, is uniquely determined by equivalence. On the other hand, the couplings to the torsion tensor is not determined by the equivalence principle. Okay, so it's basically like a matter field because it is not, there's no universal rule for coupling the torsion. So instead of working with the Levi-Civita with the connection with the non-vanishing torsion, we can just work with the Levi-Civita and put the extra torsion field as an extra matter field, which is the 1,2 rank tensor field. Okay, so that's why we work with the Levi-Civita with the torsion-free connection. Okay. All right. So let me give the summary and the outlook. First, we worked out the Newtonian limit of the geodesic equation. Remember, the geodesic equation is the equation of motion of a point particle in curved spacetime or a Riemannian manifold, which represents spacetime with the gravitational fields turned off. And as a result of this Newtonian limit, which is a double limit, slow speeds and weak fields, we could identify the Newtonian scalar potential with this component H00. Remember, H is defined to be G minus eta. The component of H is the component of metric minus the Minkowski metric. So Newtonian scalar potential gets identified with H00, and acceleration due to gravity G, or gravitational field intensity, is measured by this component of the Christoffel symbols I00. Next, we introduced the covariant notion of a covariant derivative of tensor fields via this quantity which is called the affine connection. This is a non-tensor or a symbol, which is an extra data on the manifold. The affine connection also allowed us to define parallel transport of vectors. So we take a vector which is in a given tangent space, and then we could define a notion that on a curve, I can transport the vector parallel to itself to another point. So this was facilitated by the affine connection. And the affine connection also allowed us to define autoparallel curves, that is, the straightest line, analogs of straightest lines. Then we considered a special connection which is metric compatible and torsion free. This is called the Levi-Civita connection, which can be entirely solved in terms of the metric and its derivative. The connection which is derived from the metric, like so, is called the Levi-Civita connection, and this is what we will use in derivativity. So in the next lecture, we will introduce some very crucial topics. First, we will look at something called the geodesic deviation equation, which will introduce the Riemann curvature tensor. Now this will be in Newtonian gravity. This would be the tidal forces. So we will look at two geodesics and how they separate, and the rate of their rate of acceleration of the separation will give us the Riemann curvature tensor. We will study some properties of the curvature tensor, and we will define certain parts of the Riemann tensor which has its own utility or own importance, which is called the Ricci tensor and the Ricci scalar. And finally, we will write down the Einstein field equation. With that, I will say goodbye and see you next time.